Let us look at heritability, estimating phenotypes, and response to selection. Heritability can be defined as the proportion of genetic variance to the total variance. Let me put a laser pointer. So heritability, we can define it as the proportion of the genetic variance against the total variance. So we normally have two specific types of heritability that we can estimate. We have broad sense heritability and narrow sense heritability. So the broad sense heritability is the ratio of total genetic variance to the total phenotypic variance. Remember, we have already looked at the total genetic variance, which is given by Vg, and the total phenotypic variance, which is given by Vp. Okay, so the broad sense now takes total, because we said genetic variance can also be attributed to additive, dominance, and interaction variances. So broad sense then means all these factors over the total phenotypic variance. But now narrow sense heritability then is the ratio of the additive genetic variance alone, because this is a component. The VA is a component of VG. That means we are just taking one portion and ignoring the dominance and ignoring the interaction variance that is caused by things like epistasis. So then that makes it narrower, because we are only looking at the additive, okay, against now the total phenotypic variance. So we have the two, broad sense and narrow sense, and you can see that for broad sense is given by capital H to power 2. The narrow sense is given by small h to power 2. So the heritability does not indicate the degree to which a trait is genetic. Rather, it is measuring the proportion of the phenotypic variance that is resulted by genetic factors. Okay, so it's not looking at how a trait is genetic, it's looking at within this phenotypic variance that we have in our population, what is the proportion of that phenotypic variance given by genetic factors. So heritability estimate is specific to the population and the environment, of course, that you are analyzing. The estimate is a population, not an individual. So we don't look at individual parameters, we are looking at a population parameter. So just to recap, when we looked at how we get the number of genotypes, we said that the number of genotypes is given by 3 to power n, and n is the number of genes that have been involved in the expression of that trait. And we looked at this table, yeah, of the various genes versus the many genotypes you're likely to have. So this table shows that with more genes involved in a trait, then many possible genotypes are expected. So if we have determined the narrow sense heritability of a trait, and we know the several population values, we have some values within the population that we know, then we can be able to estimate the phenotypic value of an offspring. So the formula that can be used for this prediction is, so in this case we are saying we have the narrow sense that is as a result of genetic factors, the additive genetic factors. Then we have some population values. In this case, we have like the population mean. We already have obtained the narrow sense heritability that is gotten this way. And then we have what we call the mid-parent value. So if we have all this data, then we can predict the offspring phenotype. So in this case, we are saying we are now starting from, we do not know the phenotype of the offspring. In short, we have parents. That's why we have a mid-parent value. We have the parents, and we would want to know what phenotypic characteristics would our offspring have. And this is important in research in biotechnology because you are able to predict, okay, if I mate this parent and this parent, my offspring will have these phenotypic characteristics, and you can check whether they are desirable to you or they are not desirable depending on what is your end goal. So this is a very important formula. So once we use it, then we are able to get the prediction of the phenotype of the offspring. So for example, this is an example where we have T representing 80 seeds per plant. So the phenotypic characteristics of this particular plant, we have the T as 80 seeds per plant. We have the TF. So we have the TF. TF is you remember we had the TF and the TM, so the mid parent value. So we have the female and the male value, then you divide that by 2. So we have the T, we have the TF, we have the TM, we have the mid parent value, which is 90 plus 120 over 2, giving us 105, and we have the narrow sense heritability. So then the offspring phenotypic value can be estimated by 80. Yeah, remember our formula, which has the population mean, which is 80. Then we have the heritability, narrow heritability, narrow sense heritability. Then we have the 105 minus the mean for the population. And of course, now we get that our offspring will have like our offsprings from this generation will have an average, because it's not an individual plant, it is within the population, the average. So the average of now our new offspring should be 92.5 seeds per plant. This is good because it's actually an improvement from the population mean, which was 80 seeds. You can see that we have improved from 80 to 92. You see, that's what I was saying, that when you have parents, then you can be able, you have selected the best parents out, which has 90 seeds and one with 120 seeds per plant. And you can see that within the population, this is the mean. But now we have obtained a new mean of 92.5. So on average, the population that is derived from mating these two parents will have 92.5 seeds per plant. Note that each plant in the next generation will have this. It is the average of now the new generation, which is a good thing. Then within that, it means that some plants within this other new generation will have even more than 92, others will have less than 92, but on average they'll have 92.5. And that means you can keep improving. Now from this generation, you can pick the best from this generation, then you combine them, and so on and so forth, and keep improving. That's how we improve plants, that's how we improve animals with time. So remember, the quantitative traits are affected by the environment, and the environment will be responsible for any deviations that now we would see from this estimated phenotype. So now, if you find now deviations from 92.5 to the 100 seeds per plant, or the 70 seeds per plant, then it means that now the factors that are coming in are not genetic. Now those are environmental. So remember, heritability was helping us to determine those that are of genetic contribution. But then those that now vary from here up or down will then be as a result of our environment. Then another thing we can do is predicting response to selection. So another use of heritability is to determine how a population will respond to selection. So typically, parents with the phenotypic value of interest are selected from a base population. Yeah, this has been used even traditionally, where we select parents from a base population so that we can be able to just observe how our offsprings will be. So these parents will be crossed and a new population is then developed. The following distributions are going to help us illustrate this point. So you have your base population, or the population you are starting with. Then of course you have the new population, the population after you have done mating of your selected parents. So now from your base population we have the mean. So we have the mean of selected parents. So we have the mean when you are starting, and then you have the mean of selected parents because you have picked parents from this part of your population who have best characteristics. So the selection differential, what you call selection differential S, is given by the mean of the selected parents minus the mean of your base population. So the selection differential is the difference of the base population mean and of course the mean of the selected parents. Then now in your new population, of course, you have now another mean that you will get, which is indicated here, the now new mean of the offspring of the selected parents. So the selection response, so now this is the selection response. You have selected, mated, and this is how now this new population looks like. So what is their mean? So the mean selection response R is given by now the new mean of the offspring of selected parents and minus the base, the mean of the base population. Then how we get now heritability in our narrow sense heritability, we now will get it using R, which is the selection response, over the selection differential. Okay, so the one that we are getting from the new mean of the selected offspring of the selected parents minus the base population, then you divide by the selection differential which you're obtaining from the mean of selected parents minus the mean of the base population. Then the selection response is now how much gain do you make, because when you're doing selection you must be gaining. You don't just select, you select the best within the population, so that you look at, if I mate these best parents, what kind of gains do I get in the new offspring. So it's a gain. Of course, maybe if you lose, then it means that there might be other factors. The selection response is then how much you gain, how much gain you make when you mate the selected parents. And remember, the narrow sense heritability is a measure of the genetic component that is contributed by the additive genetic variance. We are looking at the additive genetic variance because we are looking at gain. Okay, so then the response to selection can thus be derived by multiplying the heritability by the selection differential here, this equation. Okay, so you can see that heritability has also helped us to determine the response to selection within a population. And here we have an example. So the base sunflower population has a mean of 100 days to flowering. Two parents are selected that had a mean of 90 days to flowering. The quantitative trait days to flowering has a heritability of 0.2. What would be the mean of a population derived from crossing these two parents? So R is equals to H2S. So R is 0.2. Then we have the parents mean, which is 90, minus the base population, which is 100, giving us an R of minus 2 days. So the new population mean would therefore be 98 days to flowering. 98 days to flowering, which is 100 days of the base population minus the 2 days. So we have gained by reducing the days to flowering by 2, at least by 2 days. So you can see what we mean by predicting the response to selection using heritability. Yes, that is it on that. How we can use heritability to get the phenotypic value of offspring and also response to selection.